In this video, we'll look at some other examples we can encounter when carrying out integration by partial fraction. Now, in this case here, we want to consider the time when the denominator q of x contains an irreducible quadratic factor or factors, none of which is repeated. That means we don't have any 1 to the power raised to the power of 2 or more. So if qs can be factorized into as squared plus bx plus c such that b squared minus 4ac is less than 0, that means this quadratic factor is irreducible. We talked about it in an earlier video. In addition to the partial fraction we have seen earlier, that is the linear decomposition of the expression rs over qx, we will have a term of the form ax plus b all over this irreducible quadratic term, where a and b are constants we need to determine. For example, assuming that we are given a function f of x equal to x over x squared x plus 2 multiplied by this whole thing. Notice that everything in the denominator here is irreducible. This is a linear irreducible term. This is a quadratic term which can be shown to be irreducible, and this is also irreducible. That means this here cannot be decomposed, like we can't factor anything from this denominator again. To decompose this into partial fraction, the theorem says that the linear factor we write as a constant all over the linear term, and then for the irreducible quadratic term we are going to have a linear term above. The degree will be 1 less than the degree of this quadratic term, so that's why we have bx plus c all over the irreducible quadratic term plus bx plus e all over irreducible quadratic term. So whenever you have an irreducible quadratic term, to decompose that into partial fraction, you write a linear function at the top, and then below will be the irreducible quadratic term. Okay, if we are able to do this, we can integrate the term containing this quadratic or irreducible quadratic expression in the denominator by completing the square if it's necessary, and using the fact that integral of 1 over x squared plus a squared dx is equal to 1 over a inverse tan of x over a plus a constant c. We saw this when we are talking about trigonometric substitution, I think, or trigonometric integrals. Okay, let's look at an example. Imagine we are asked to integrate this. To be sure that I'm recording. Okay. Imagine we are asked to integrate this function given in example 5. First thing we need to do is to factorize the denominator here. Why is that the first thing? This is a proper fraction. So since it's proper, we don't need to carry out any long division. The degree of the numerator is 2, the degree of the denominator is 3. So the degree of numerator is less than the degree of the denominator. We can now split into partial fraction. So notice that this is too big. Notice that x cubed plus 4x is the same thing as we can factor x out to get x squared plus 4. And at this point, we can't factor this any further. So that tells me that my 2x squared minus x plus 4 divided by x cubed plus 4x is the same thing as 2x squared minus x plus 4 divided by x into x squared plus 4. Now, partial fraction decomposition theorem says that we can write this as a constant over the linear factor plus a linear factor all over the irreducible quadratic factor. Our work now is to find what the constant A, B, and C would be. Anyway, if we write this together, the LCM of this is going to be x into x squared plus 4, and then divide x by this and multiply the quotient by A, we get A into s squared plus 4 plus bx plus c multiplied by x. This is what we get when we combine this together. Now, since the denominator of this and the denominator of this are the same, we can equate their numerator. So this implies that 2x squared minus x plus 4 is equal to A into s squared plus 4, then plus b x plus c into x. Get some water. Okay, now here I'm gonna use the other method of expanding and then grouping like terms and equating coefficients. This will be equal to as squared plus 4a plus bx times s is bs squared, then plus cx. This would be equal to the terms containing s squared are a and b, so I'm going to have a plus b into s squared plus cx only has this, and 4a is the constant. Now, since these two equations or expressions are equal, they are polynomials. For them to be equal, their constants or coefficients must be the same. That means the coefficient of x squared and s squared here must be equal. The coefficient of x here and x here must be equal. The constants must be equal. So this implies equating coefficients. We have that 2 is equal to a plus b. This will be the first equation. The second equation, -1, which is the coefficient of x, is equal to c. And the third one is 4, the constant is equal to 4a. So basically we found our c and our a is equal to 1. If a is equal to 1, my b will be 2 minus a, which is equal to 2 minus 1, that's going to be equal to 1. So my b is equal to 1, my a is equal to 1, and my c is equal to -1. With these constants found, we can now proceed to integrate this function. So the integral of 2x squared minus x plus 4 all over s cubed plus 4x dx is equal to the integral of a over x. My a is 1, so I'm going to have 1 over x, then plus bx plus c. My b is 1, so I'll have x. 1 times s is x, and my c is -1 all over s squared plus 4 dx. Now we can integrate this term by term integrating term by term gives me the integral of 1 over x dx. This one here, I would like to split it into 2. It will be easier for me to split this into 2 to get x over s squared plus 4 minus integral of 1 over s squared plus 4 dx here. Integrating each term, I get ln of x plus, if I integrate this, I'm going to get 1/2 ln of s squared plus 4 minus, if we integrate this term, we'll get 1 over 2 inverse tan of x over 2, then plus a constant c. So in conclusion, my integral that I had earlier, which is this, is equal to whatever I get after carrying out my partial fraction decomposition. S squared plus 4 is actually positive for all x, so we don't need absolute value here. And then minus 1/2 inverse tangent of x over 2 plus a constant c. I didn't really go through the process of integrating these terms because I believe at this time each of us knows how to integrate things that looks like this or something that looks this way. That's why I just quoted the integral that way. Let's look at another example involving this kind of thing, but this time around maybe involving a fraction that is improper. Now notice that this fraction here is improper because the degree of the numerator and denominator are actually equal. It will be proper if the degree of the numerator is less than that of the denominator, but that's not the case. So we carry out long division. We need to carry out long division here, and that is what I'll do right now. Long division, outside I'm going to have the divisor, which is 4s squared minus 4x plus 3. Then inside I'll have the numerator, which is this. I'll divide the highest powers. So I'm going to use this whole thing here to divide this to get 1. I'll use 1 to multiply through everything here and write it below here. Plus 3. I'll subtract. If I subtract, 4x squared goes. I'm going to have minus 3x minus 4x. That will be minus 3x plus 4x. That would just be x. And then I have 2 minus 3 will be minus 1. So that tells me that my 4x squared minus 3x plus 2, actually here, this highest power cannot divide this any longer. So our division stops there. This would be equal to, our quotient is 1 plus our remainder is x minus 1 all over the divisor, 4x squared minus 4, is that 4? Yes, plus 3. So the next thing I'm going to ask myself is, this is a proper fraction. Is it possible for me to factorize what I have below? Is it reducible? Is it not reducible? Well, for me to check, I'm going to check whether my b squared minus 4ac is actually less than 1. I'll do that somewhere. So my b squared is going to be minus 4 all squared minus 4a here will be 4 and my c is 3. That will be equal to 16 minus 16 times 3 is less than 0. So that tells me that my 4x squared minus 4x plus 3 is irreducible. So now I need to integrate this way. For me to integrate it this way, I would need to complete the squares, because that would give me as this thing here as something squared plus or minus another thing squared, which I know how to integrate. So completing squares, I have that 4x squared minus 4x plus 3 is equal to, I can factor out the 4 first and get s squared s squared, is that plus or minus? That's minus x plus 3. This will be equal to 4 into, I'm completing the squares now. I'm completing the squares. I think this is really not necessary. Is it? I don't think it is. Like, merely looking at this thing, I believe there is something smarter than I can do, that I can do to get this. You can actually complete the squares, that's perfect, and get some answers, that's cool. But I just want to let you know that there are some better things you can do. I know that I can write this as 4x squared plus or minus, please, minus 4x plus 1 and then plus 2. I split my 3 into 1 plus 2. This thing here is the same thing as 2x minus 1 all squared. I just saw that and looked like this looks cool. Then plus a constant 2. So here I've been able to complete the squares without really doing anything much. You can still get an equivalent of this when you go through the procedure you want to go through. So getting this done, let me see whether I have enough space to complete this. Okay, I do. I think I made the space for this. So my integral, I'm just going to call this integral I. I don't want to start writing this again. You can do this if the integral is too much for you to write, that you to take your time for you to write. Just call it I and then start referring to it as I from that point. So my I, which is the integral of that, will be the integral of 1 plus x minus 1 divided by 4s squared minus 4x plus 3 dx, which is the same thing as integral of 1 plus x minus 1 all over our completed square will be 2x minus 1 squared plus 2 dx. We are now charged with looking for a way to integrate this here. There may be several ways you can do this and arrive at the same solution, but the easier way is to first of all at least make this to be only one variable, and that would help you to solve. So I'm going to do the u sub, let u to be equal to 2x plus, why am I always writing plus, 2x minus 1. This tells me that my du will be equal to 2x dx. Will be equal to 2x dx. Is that correct? No, it's just going to be equal to 2. This means that 1/2 du will be equal to the x. Now, if here my u is equal to 2x plus 1, that means that my u plus 1 is equal to 2x, which implies that x is equal to u plus 1 over 2. Now, why am I doing this? Well, I know I have some x minus 1 above, and if I'm changing the variable, I'm still going to change the variable of x above. So my integral I, which is equal to this, becomes, by doing change of variable, I'm going to get 1 plus, I think this 1, I can just leave it with the x. Yeah, I can just leave this one with the x, so I just work with something else. 1 dx plus, then I'll change the variable of this one to u and work with that. So changing to u, my x is u plus 1 over 2, and then I have minus 1, so my x minus 1 becomes this whole thing. Below, I'm going to have u squared minus or plus 2. And then my dx is 1/2 du, so I can actually write that 1/2 outside and then have du here. Let me put this inside the bracket to make sure everyone knows what it is. If I integrate 1 dx, I get x. I can simplify this thing here to be u plus 1 minus 2 over 2, and that over 2 can come outside to become 1 over 4. So this will be 1 plus 1 over 4. Simplifying this gives me u plus 1 minus 2 is just going to be u minus 1, right, over u squared plus 2, and then du. I can integrate this by splitting it into 2. It's usually easier to do it that way. Plus 1 over 4. I have integral of u over u squared plus 2 du. This can be integrated using a u sub or maybe a v sub this time around, since we have u already. Minus 1 over u squared plus 2 du. So if we use a w sub or anything sub, this integral becomes x plus 1 over 4. If we integrate this, we're going to get, I think, 1 over 2 natural log of u squared plus 2, right? And if we integrate this, we are going to get 1 over square root of 2 inverse tan of u over square root of 2 plus a constant c. But we need to take everything back to u. So back to x rather. My integral I, maybe I can rewrite this integral. My I, which is my original integral, which looks like this, will be equal to x plus 1 over 4 into 1/2 ln of u squared plus 2 is this thing u squared here, this whole thing here squared plus 2, which is what we have at the denominator as qx. So you can either write it as 2x plus 1 all squared plus 2, or you can write it as 4x squared minus 4x plus 2 or 3. Minus 1 over square root of 2 inverse tan of my u is 2x minus 1 divided by square root of 2. And then plus a constant c. And this will be all about this integral. So we see that the bulk of the work involved here maybe what you need to do before the integral becomes as simple as what you can or what you're used to, or maybe what you know before. I think I would like to point out something here. Generally, if we are integrating rational function of the form a squared a plus b all over s squared plus bx plus c, where that is irreducible, where my b squared minus 4ac is less than 0, that means this is irreducible, then we proceed by completing the square of what we have below. And then after completing the square, we can make appropriate substitution, say complete square of as squared plus bx plus c, make appropriate substitution, just like we substituted u equal to 2x plus 1 above. Substitution to get an expression of the form, maybe cu plus d divided by u squared plus a squared du. If this is the case, then we split this integral into two. We split it into integral of cu over u squared plus a squared plus integral of d all over u squared plus a squared. This can be solved using a u-solve, and this is the same thing as the integral, or the integral of this is the same thing as inverse tangent. And with that, we can get that the solution will be c over 2 ln of u squared plus a squared, then plus d over a inverse tan of u over a plus a constant c. This is usually what you get whenever you encounter integral involving this kind of expression. I hope you recall this and use it when necessary. Now, we've seen how to solve when the denominator has an irreducible quadratic expression or factor. What if we have like multiple or repeated quadratic expressions that are irreducible? How do we integrate such expressions? That is what we'll be focusing on the next video.